All right. So I'm going to be talking today about the BOSS microphysics framework. This is work that I did at Columbia University with Marcus van Leeuwenhoek and Hugh Morrison at INCAR. I was a postdoc there up until August when I joined PNNL and started working at Hu Yuan's SciDAC 5 project. But this is what I was working on just previous to that. So today I'm going to talk about first of all, I'm just going to give an introduction. What is BOSS? Then I'm going to talk about some results that we have using BOSS to produce a bulk scheme that emulates the tau bin scheme, microphysics scheme in an unidealized 1D driver, and then get into what further steps are, things that have happened since that work, and that are next steps moving forward to eventually get this to be a useful microphysics scheme in weather and climate models. So first, just to say what BOSS stands for, BOSS is the Bayesian Observationally Constrained Statistical Physical Scheme, which is actually kind of a family of microphysics schemes developed with similar methodologies. BOSS schemes are data-driven, a form of supervised machine learning. The input data can theoretically be any output of a model that implements BOSS. So it could be something as direct as the process rates themselves, or it could be something like averaged outputs from climate models or data from an instrument simulator. That said, we will say how to best combine or weight data from very different types of sources is not really settled, and so that's kind of an ongoing area of research. The other thing I should point out is that BOSS schemes are not black box. This is not like a random forest or neural network where it's just inhumanly complicated to figure out what's going on inside of it. The process rate equations in a BOSS scheme can be written down in 1 or 2 pages and look like those of traditional parameterizations. The difference is really just the large number of adjustable parameters, which requires this kind of data-driven approach. So to briefly describe what a bulk microphysics scheme is, or what it's trying to do. So if we think about and here I'm just going to be talking about liquid microphysics. If we think about the number density of droplets as a function of drop size, that's the drop size distribution, or DSD. And the moments of that distribution are what are typically used as prognostic variables by a bulk microphysics scheme. And part of the reason being that the moments of that distribution typically have very physically comprehensible meanings. So the 0th moment is total number. Assuming spherical drops, the 3rd is proportional to total liquid mass. 6th is rate of reflectivity factor, and so on. So the goal of the microphysics scheme is to evolve those moments in time. So the rate of change of the moments is going to be the sum of the effect from process 1 plus process 2, and so on. So for most processes, BOSS use sums of power laws. So for instance, the collision coalescence is a pretty typical example. The rate of change of a given moment due to collision coalescence in BOSS is going to be sum of power laws, where each power law is going to be a coefficient times a product of the moments raised to some power. And these coefficients and exponents in the equation are the parameters that we have to adjust. And then for sedimentation, we use a similar formula for fall speed and then solve the typical PDE for sedimentation. The way BOSS schemes are developed in generally is you get some data that you're going to use for training the scheme and for evaluating it. You choose the prognostic moments that you're going to use, and then you choose an ensemble of power rate formulas with some moderately large number of adjustable parameters that is the set of functional forms for predicting those moments in time. So those are the sums of power laws that I just mentioned. Then you choose an error model, which is kind of a probability distribution that you assume for the model data discrepancy. And then we use Markov chain Monte Carlo to find the probability distribution of parameter values via Bayesian inference. Because it's a Bayesian method, you need to input some prior distribution. You usually use a pretty weak prior so that the output is very much determined by the data set that we're using. The maximum likelihood estimator, or MLE, gives us a sort of best fit or best set of values. We also get this benefit of uncertainty quantification via having the whole posterior probability distribution to work with. So I don't have time to explain how the MCMC algorithm works in detail, but in essence, there's this loop of where you have some generator for a set of parameter values. You feed that into the physical model that's running the BOSS scheme and predicts some set of observed values. You have an error model that takes those predictions and the actual observations and it predicts the likelihood of the observations given these proposed parameters, and that likelihood is used to accept or reject that parameter value. If it's rejected, we just ignore it. If we accept it, then we use it as a starting point for guessing a next set of samples. Stochastic algorithm that outputs a set of parameter values that are sampled from the posterior probability distribution. And then also something that I don't have time to get into in detail, but there are some physical and mathematical constraints on the process rates. So I showed you general power law sums as kind of our functional forms that we assume, but we can actually eliminate some parameters or constrain some of those power law forms, which is beneficial because it lowers the dimensionality in which we have to work with MCMC. It might condition the problem better. It's computationally cheaper, produces simpler formulas in some ways. And so the two constraints I'm going to highlight, first of all, a lot of the microphysical processes have certain scaling behaviors. So for example, there's a scaling symmetry for the stochastic collection equation that covers collision and coalescence. And also the moments have to correspond to a valid distribution. So for a 3-moment scheme, you can actually calculate the variance and standard deviation, and those have to be real positive quantities. And that's actually a constraint that can affect the equations that you pick. So with all that background out of the way, I'm going to talk about this particular set of experiments trying to emulate the Tel Aviv University bin model. So this is kind of a proof of concept to see if BOSS can actually handle complex microphysics problems using this approach. So the tau bin model output is used as our source of observations or truth. The emulation is only of liquid microphysics, and we emulate non-precipitating and drizzling stratocumulus regimes as represented in a 1D kinematic driver. So before getting to the BOSS results, I'm just going to show what this looks like in the bin model. On the right here, you have height versus time plots. The top is cloud mass over time. The bottom is rain mass. And this is a 1-hour simulation where we have this forcing that's basically a 20-minute oscillations of an updraft, downdraft, downdraft. That's condensing cloud 3 times, and then that cloud drizzles each time it forms. This is the case that I'm going to be focusing on, which is a relatively heavy drizzle, because the more rain there is in general, we've found, the harder it is for the to emulate what it's doing, and the more interesting spread there is between models. So this is the particular case I'm going to show, even though we have 8 different cases being used, not all of which produce drizzle. There's 6 different BOSS simulators that we used to try to get a bulk scheme to fit the spin scheme. Half of them are 2-moment schemes, like MG2 or P3. They've got 2 cloud moments, 2 rain moments. The same ones used by those schemes, and those are, we label them just the 2M schemes. The other half still have 2 moments for rain, but they have 3 moments for cloud, and so we label those the 3M schemes. Those are the 0th, 3rd, and 6th moments for the 3-moment schemes. And then for each of those types of schemes, we have 3 BOSS schemes that use different auto-conversion formulas. So we have a single power law term where auto-conversion of cloud to rain is given by a single power law term. So that's kind of like what the Kudnev and Kogan or KK2000 scheme does. That's currently in E3SM. There's also in our 2T, which uses 2 power law terms that are, both have independently tunable parameters, and then a rain-dependent scheme where we have 2 terms, and then one of them can actually depend on the moments of the existing rain as well. So the first versions of these boss schemes are tuned as using kind of a traditional method that's kind of reminiscent of how KK2000 was actually tuned up in the first place, where we just treat the moment values and inputs and process rates diagnosed from the bin model as outputs, and you just try to predict that function. So it's kind of a simple regression problem, although we're using this Bayesian method to do that. And so if you look at the best fits from that, all schemes perform fine for non-precipitating cloud, but in these rain cases, we really find they struggle. So on the right here, I have the top plot is rain water path over time. This column integrated value. So the black line is the bin model, and then our 6 BOSS models described here are all of the colored lines, and you can see they do pretty poorly. They almost always underestimate rainwater path significantly. At the bottom, we have surface precipitation rate, and that does better, but in most schemes at least, but that's probably compensating errors of it producing too little rain, but then making too much of that fall out, and so you get sort of approximately the right surface rate for some of these schemes. But we're not particularly satisfied. The problem here really seems to come from the auto conversion, which is part of the reason that that's the main thing that we varied in the first place with trying these different schemes. So on the left here, I've got column integrated auto conversion rate over time, same color coding as before. You see none of the schemes, they're really not in agreement with each other or with the bin model, despite being all trained from the same data. And then this second plot is the same thing, but at a later time. So this is the first oscillation in that hour-long period, and this is the last one. And so there's too much sensitivity for most of these schemes to precipitable water, which is the main thing that differs between these cases. And also, they're just not that similar to the bin scheme in terms of their timing and so on. So we attribute a lot of this problem to the fact that fitting instantaneous process rates offline like this is kind of known to be insufficient, or at least to often go wrong. Really well known now, or at least recently, paper that mentions this is Seifert and Rasp, where they produce neural networks that are very highly accurate offline emulators of a super droplet scheme, but they do worse than a 2-decade-old traditional scheme that's been tuned to capture timing of precipitation, and the neural networks can't really reproduce that. We also kind of want to move away from just having to fit using process rates, because those are not really directly observable anyway. So we try training BOSS using its performance in the 1D driver rather than just on these using this offline method. So in the interest of time, I'm not going to dwell on this too much, but essentially we use pretty sparse observation set where we don't use every grid point at every time. We just select specific observation times in the MCMC algorithm, and we observe quantities like the cloud and rain moments, not things that are unobservable like the process rates. And so for these schemes, which we call the TE schemes, or time evolving tuning schemes, we do much better. So this is the same graph as I was showing before, but for the TE schemes, and we see that the BOSS rainwater paths are much closer to the bin model output. The surface rain rate is also a bit better, but more importantly, we know that when it does well, that it's more likely to be due to something that's kind of physically reasonable because rainwater path is good. This better performance is not surprising because this is much closer to what we were training or the models to do effectively. But it is good to know that it's actually possible to get to much better performance using these formulas. I also, the light blue versus the pink here, I'm just showing the difference between using 2 different methods of selecting the prior. We do that mainly to show that the Bayesian prior that we're putting in doesn't actually have that huge of an effect. If we look at on a process level performance, auto conversion, for instance, does much better with these schemes. So first of all of the schemes get timing of auto conversion much better with the time evolving tuning. There's with a lot of the schemes, they tend to overestimate the peak, but this is also getting into the regime or the period of time when accretion starts to take over as one of the main rain producing processes, so that may not matter as much. And also some of the 3-moment schemes actually match very closely um, at all times and whenever we're checking on the auto conversion rate. So specifically, the 3-moment schemes with 2 terms um, do fairly well with that. And just to show that in a little more detail, I know there's a lot of information on the screen, so I'm just going to go column by column and discuss what these are. So here I'm just showing for the bin model in the first column, first the rain mass, and then each of the, on these height versus time diagrams, and then each of the process rates, so auto conversion rate for rain mass, accretion, rain evaporation, and then mass weighted fall speed. And so if you look at the second column, that's the 2-moment rain dependent. So this is the best 2-moment scheme that we had. And it does pretty well with the placement of these process rates, but tends to overestimate all of them. So producing too much rain, then evaporating too much of it, and it kind of evens out to getting reasonable results in most places, but not perfect. The third column is the best 3-moment scheme we have, which is 3M in R2T. And that is actually just by the eyeball norm. You can see that that is very close in terms of the auto conversion, accretion, and evaporation rates. And then these last columns actually show the differences. So again, the 2-moment scheme is overestimating pretty much everything, maybe underestimating fall speed a bit. The 3M is much less error and also less clearly biased in one direction or the other. So the remaining deficiencies of these time evolving schemes, mainly it's just that the 2-moment is still not perfect at handling auto conversion. In Seifert and Rasp, they suggest that for a 2-moment scheme, predicting auto conversion may actually be kind of ill-posed in some regimes. This is backed up by a paper by Adele Eigel, working with us last year. And she's done a lot of work looking at issues with having a 2-moment, 2-category scheme. And then also cloud number evaporation is difficult to model accurately. That's not a huge deal for GCMs or climate models, but it is a kind of a difficult thing to do. And then finally, all of these schemes have only 2 moments for the rain. We know that that causes excessive size sorting in the sedimentation. And that ideally you would have at least 3 rain moments to do that well. So just wrapping up here, talking about what's next for BOSS. I'm gonna, again, in the interest of time, just kind of go through this very quickly. First of all, we've developed a single category version of BOSS that uses the 0th, 3rd, 6th, and 9th moments of the full distribution rather than breaking the liquid into separate cloud and rain categories. So on the bottom right here is a drizzling case where I'm comparing a 2-moment, 2-category scheme, actually the 2MRD that I showed earlier, to this 4-moment scheme. It does kind of comparably, maybe a little bit worse in that context. I think partly this is just a newer scheme. I haven't really figured out how to deal with evaporation well. Top right is showing a different experiment where we tried using this scheme for heavier rain events. And we actually see a pretty big benefit for the 4-moment scheme there, the single category. Also say that there's that these both the 2-category and single category versions of BOSS have been implemented in the CM1 LES model. Caitlin Loftus has recently started working at this at Columbia, and then Hugh and Marcus are still involved in that. I've kind of just been watching from the sidelines since I'm no longer directly involved with that. But there is an ESMD effort to train BOSS, particularly for single category in the LES context, which requires some new emulators because the LES is too expensive to run MCMC on directly. And the goal with this LES work is that now that we know that we can do this simple 1D case to do a case with more realistic drop size distribution and spatial variability, and to use maybe that LES data will help us to scale that up because that gives us information about subgrid scale variability that would be helpful to scale up to climate model resolutions. I'm not going to go into the details of GCM integration right now because of time, but there's some new questions that have been raised and need to be solved. Just for kicks, I did implement BOSS in E3SM v2. I wouldn't say that the results are great because there's no accounting for subgrid scale variability in these runs, but surprisingly, very quick to, I guess I shouldn't have been so surprised, but it's very quick to implement because the equations are relatively simple. And it doesn't do terribly. It's just, uh, not, it has some unusual features because it's, um, again, I think that it's not accounting for subgrid scale variability of water mass. And finally, just mentioning this BOSS work has all been using very short time steps. Even the plots that I just showed were really reducing the E3SM. Sorry, this was for like a single column model. I did some tests. Those are using a very short time step of 5 seconds. We could go a little bit higher, but there's still a pretty big gap between that and where we would like to be. The computational cost we would like the microphysics to have requires a longer time step. But we also know that the existing schemes, MG2 and P3, are not really that accurate for the time steps that we're running at. So there's kind of a general time resolution issue in the microphysics. So the new project that I'm involved with is this SciDec5 project, Pascal, that is Hui Wan will be talking about, I think, in this meeting in a few weeks. And that's revising time integration and process coupling in E3SM. And as part of that, I'm planning a new coupler and integrator written in C++. Initially just for P3, but allowing other microphysics schemes to be swapped in, including potentially BOSS. So that's all I have. And at this point, I'll take any questions.